Okay, so today I want to drive you through a new lemma because we need it for the converse. To prove before the weak converse of the achievability of our Schumacher's theorem, we need the continuity of conditional entropy lemma, which is called Aliki Fones Winter AFW. So if we let two quantum states, it can be represented by density matrices, and epsilon being superior to 0, it means that if we have the one minus the other, then we can write if we have number 2, the trace norm of both of them being inferior to epsilon, which is inferior to 1, which means both of them are less or more close to 1 of each other, then their entropy too will naturally move a lot. So it basically says that this entropy is a continuous function, you will not have a huge gap if you have of the entropy if you have the states being less or more the same. Where I is the binary entropy. So yeah, to explain you a little bit better, so as I said, this is just why it cannot take it like this. It's just representing the distance as the norm trace distance, like the trace distance between two states between being the maximum epsilon. So this means rho AB and psi AB are indistinguishable with a probability superior to 1 minus epsilon. Because because of this. That's the main point first. Second one is the entropy, the conditional entropy, because the states cannot be differentiated by epsilon, that's the difference between both. It means it's just you can't distinguish them 1 minus epsilon because all this stuff how to say because we cannot distinguish them with epsilon, it's how to say it, we have your two states, the first one, the second one, and so the two there is epsilon between them, and so it means all the stuff where you have stuff that are in a way bigger than epsilon, you can distinguish them, but the stuff where you cannot distinguish them, or it means if the difference is epsilon, then it's 1 minus epsilon, because I'm trying to explain it well. The analogy is you cook something and you have two ways of doing it, and it's 99% equivalent, then it's alright, but if there is 1% difference, then it means it's this 1% is the epsilon. Then if they are identical to 1 minus epsilon, which is 99%. So that's the same principle here about it. And we have this. We have also R2 the symmetry is AB composed of two systems A and B. H, the entropy of A knowing B, it is entropy of rho AB minus entropy so rho B, because it's the entropy of the system minus what you know, so rho B. And so it's like you have this entropy of AB knowing B is like it just this like, and so it just this, and so all the system minus this system, so h of rho AB minus h of rho B. T is the dimension of the Hilbert state, h of rho is the entropy, is general entropy. And we see that when the difference goes to of epsilon goes to 0, the number at the right goes to 0. Like if we have like this, then this limits of this going to plus infinity of both of them, like it just equal to 0. Which guarantees the continuity in a way. It means like, when you have your two ways to cook, if it's like less or more 100%, then there is no really difference between the entropies. It's the same, and that's what we prove. So imagine now we take a really, I just need to put my computer into some power. So imagine now you have our stuff about it, and so what we want to do is like we want to take a concrete example about it. So let's take a qubit system, like A is a qubit, so its dimension is just 2, 0 and 1, so log of 2 of the A is equal to 1, because log of 2 is equal to 1. And so we take the maximal untangled states, which is psi plus psi plus, with psi plus being the famous Bell state, like used into the proof of our French one who contradicts the results of Einstein. So you have this, and so for this this perfect entanglement, we have -1 by that's a characteristic of quantum entanglement to have a negative value. And so because of the noise, like let's say as our two stuff or cooking stuff, we have like 1% of error, and so your two qubits are before the canal, after the canal, because like it just like you have at the beginning, like you have the ideal state rho AB, and you have your real state psi AB, and so there is like 1% of difference. And so if we apply our inequality, it is 2 epsilon log 2 of the A, which is like 2 multiplied by 1%, which is 0.01. So epsilon just 0.01, log 2 of the A just equal to 1, and so it's just 0.02. If we calculate the second term of the stuff, then we have so the formula, we put it here. So we made this. Now we made 1 plus epsilon h of stuff. So what we have like is it's like we have, so if we calculate like h of 1 plus epsilon. So before we do like epsilon 1 epsilon, it's like 0.01 on 1.01, which is less or more equal to 0.0099. If we calculate the entropy about it, in just h of 0.0099, which is somewhere equal to minus 0.0099, like 2 of 0.0099 minus 1 minus 0.0099, because the definition is like rho log rho minus 1 minus rho log 1 minus rho, which is this. And so we have this on the just 0.0, and so it means like 1 plus epsilon multiplied by h epsilon 1 plus epsilon just equal to 1.01 multiplied by 0.00792, which is 0.0800. And so our global result is just h of b, or ib, minus h a of b of cab, which is inferior to 0.02. So our first term minus the second term plus and even if it is a minus, as we see in the other video, like it's still the one plus the other one, or I explain you, like, because the h of x plus h of y, like here it's the x here or y here, but yeah, so it's plus 0.08, so it's equal to 0.10, and so it means that even with noise, the conditional entropy of our noise system still be between minus 0.9 and minus 1.10. So that guarantees that even if we have theoretically little error of transformation, physical transformation, that does not really destroy totally, like, brutally, the property of transmission of information that we use, for example, to demonstrate the reciprocity of the theorem of the capacity of our quantum channel. So yeah, the main goal is just to say that the entropy like is continuous, and so when your state is less or more disturbed, like your entropy will be less or more disturbed, but not like equivalently. Not if it's a little, it will be a little. If it's like less or more equivalent, it will be less or more equivalent.